Learning Outcome 7.4. Determine the reconstructed signal and its spectrum. Hopefully by now, the fact that sampling is multiplication of a signal in time with an infinite pulse train is a concept you're getting used to. And hopefully you now are realizing that the spectrum that comes out from it is periodic and takes our initial spectrum and repeats it every omega s units apart. Now comes the question, if we have this as our output, what can we do with it to return to our original signal? As an application sense, we can think of this as a voice recording. You have your voice recording x of t, which has a spectrum. We sample it in order to digitize it, to put it on a CD, or to send it over the internet. We now have a digital signal. What needs to happen to the digital signal such that you can listen to it in the analog sense in the future? Because you cannot listen to a digital signal. You hear in analog. This unit's going to look at how to solve this, and we're looking at it from a frequency domain perspective, therefore looking at these spectra. The simple answer is we can put a low-pass filter around our signal. All the other repetitions of it will go away. Now we are left with a single instance of our original signal, so we're doing pretty well. However, this has an amplitude of 1 over t, and we need to have an amplitude of 1. Okay, let's try again. We can solve that by putting in a filter that does not have unit gain, but has a gain of t, or following that filter, which had a unit gain, by an amplifier of amount t. This will get rid of those sidebands, all the repetitions of our spectrum, and we're good to go. We now have a single occurrence of our original spectrum, and if the spectrum matches here and here, then the time signals will match. So we're good to go. Well, let's think about it a little bit more from an engineering standpoint. This solves our problem, but we're putting an ideal filter in and we're putting things really close. Nyquist says that our neighboring spectra can be right up on here, that so long as omega m is less than omega s minus omega m, so they're really, really close, we're good. On a real sense, however, we cannot build an ideal filter. So we're going to want to leave a little bit of a gap between the end of our original spectrum and the beginning of the repetition of our spectrum. So instead of putting in this filter, we'd be better off as engineers to put in this filter. And we can only do that if there's a gap between these 2 points. Another thing to look at, if we're going to look at it from a practical sense as engineers, is that this is still an ideal filter. We're more likely to have real filters that we can put in. In that case, this gap is much more necessary in order to accommodate the fact that the filter does not immediately drop from a pass to a block. And that will enable us to get our original signal back.